All these little dots are galaxies, some of which are bigger than our own. It's amazing, it's only 320 million years after the Big Bang.
In the world of physics, there's been a long-standing debate about certain ideas. But now, thanks to the James Webb telescope, things might be changing.
The most exciting piece of this telescope, of this remarkable instrument we put in space.
Neil deGrasse Tyson recently made a statement that suggests the search might be over.
Perhaps an infinite number of them, and we have a word for this. It's called the multiverse.
The telescope's discovery has the potential to completely change how we understand the universe. So, what exactly did the James Webb telescope find, and why is it causing such a stir in the world of physics? Join us as we delve into this groundbreaking discovery and see how the James Webb finding ends debate in physics' shattering image.
The whole of the sky was filled with galaxies. There was no empty sky. This telescope's going to be phenomenal.
The evolutionary blueprint of the Standard Model. Over the last century, an extraordinary milestone in exploring the cosmos has been the formulation of the Standard Model. This model serves as a blueprint, outlining the evolution and current state of our universe. It heavily relies on Einstein's theory of relativity and acts as a key to unlocking the mysteries of the universe's growth, encompassing its expansion and the formation of immense cosmic structures. Within this comprehensive model, numerous fundamental components play pivotal roles in shaping the cosmos. Dark energy takes center stage among these components, representing a perplexing force propelling the universe's rapid expansion. Meanwhile, dark matter stands as a cryptic substance, faintly interacting with both light and ordinary matter, yet comprising a substantial fraction of the universe's makeup. Alongside these elusive elements, there exists normal matter, comprised of familiar particles such as protons and neutrons, forming the basis of what we commonly perceive. Delving deeper into this cosmic framework, we encounter neutrinos, elusive particles characterized by their minute mass and neutral charge, contributing subtly to the cosmic tapestry. Additionally, photons, the fundamental particles of light, play a crucial role in shaping our understanding of the universe's workings. This intricate Standard Model offers a comprehensive lens through which we unravel the complexities of our vast universe, presenting a roadmap to comprehend its evolution, composition, and the enigmatic forces that govern its behavior. Around 13.8 billion years ago, the universe burst forth from the scorching hot event known as the Big Bang, following a rapid expansion phase called cosmic inflation. This early expansion sparked tiny fluctuations in density that eventually laid the groundwork for the creation of cosmic structures. However, this long-standing model, which has been the bedrock of our understanding for a century, is now facing intense scrutiny. Despite robust evidence supporting this model, scientists are beginning to question its completeness. Every new piece of data collected by astronomers undergoes meticulous scrutiny within the framework of the established model to assess its coherence and accuracy. As technology advances, tools like the James Webb Space Telescope have emerged, offering astronomers a powerful instrument. Yet, paradoxically, they're also posing challenges to the Standard Model. The James Webb Space Telescope has revolutionized our understanding of the early universe, reshaping some of our previous conceptions. Let's rewind to around 380,000 years after the Big Bang, when neutral atoms began to take shape in the cosmos. Roughly 550 million years later, a pivotal event called reionization transformed much of the universe into an ionized state. This phase kicked off about 200 million years after the Big Bang, potentially signaling the birth of some of the earliest stars. The JWST's unmatched capacity to delve deeper into the cosmic expanse has brought to light galaxies from farther reaches than we could have ever glimpsed before. This breakthrough offers unparalleled insights into these primordial cosmic eras. The Standard Model of cosmology, known as the inflationary hot Big Bang or lambda CDM model, has garnered acclaim for its remarkable success in explaining fundamental facets of the universe. It's a comprehensive framework that has helped unravel phenomena like gravitational lensing, the intricate structure of the cosmic web, the evolution of cosmic structures over time, and the movements of galaxies within clusters and groups. Furthermore, it has shed light on features observed in the cosmic microwave background, a lingering radiation from the universe's early days. According to this model, as we peer further back in time and across immense cosmic distances, the galaxies we observe should inherently appear smaller, bluer, less developed, and contain fewer heavy elements. This predictive framework offers guidance as we unravel the mysteries of the cosmos, providing a lens through which we perceive the evolution of galaxies across cosmic epochs. The projected evolution of cosmic structures over vast periods aligns with expectations set by current models. It implies a phase in cosmic history known as the Dark Ages, a period far beyond our current observational reach. This era is envisioned as a time devoid of visible stars or galaxies, representing a significant transition in the cosmic narrative. Yet as scientists rigorously examine the robustness of these explanations, they've encountered conflicting evidence, plunging cosmology into a state of uncertainty. Despite the Lambda CDM model's impressive explanatory prowess, certain observations and data don't seamlessly fit its predictions. This discrepancy has triggered a crisis within the field. The theoretical predictions of this model don't perfectly align with empirical data, casting doubt on our understanding of the universe's fundamental mechanisms. This disparity manifests in various ways: unexpected structures observed on cosmic scales, irregularities in the distribution and behavior of cosmic elements, and anomalies within the patterns of the cosmic microwave background. These inconsistencies challenge the model's capacity to offer a comprehensive explanation for the observed universe. Consequently, they raise profound questions about our grasp of cosmic evolution and structure, prompting a reevaluation of our current understanding. The elusive age of the cosmos. The universe has lots of mysteries that even really smart people can't solve. One of these mysteries is how old the universe is. Figuring that out is hard for scientists who study space because they use different ways to measure it and get different answers. They're trying hard to understand why these methods give different answers. One way they try to find out is by looking at radiation left over from when the universe started. This radiation has clues about how the universe was in the beginning. Scientists use math and ideas from Einstein to understand these clues. These ideas help them understand how the universe is made. They connect things like dark matter, dark energy, and radiation to how fast the universe is growing at different times. By studying these things, scientists want to know how old the universe is. One important thing they use to study this is called the cosmic microwave background. It's from a long time ago, when the universe was just starting to form. Special maps made from missions in space give lots of details about how the universe was back then. But there's a problem. These maps don't have much information about something called dark energy. This thing didn't matter at the start, but it's a big deal now. Because dark energy wasn't a big deal in the early universe, scientists have to figure out its effects using other information. Even though this is a bit of a limitation, scientists use equations called Friedmann equations to figure out how fast the universe was growing at different points in time. This helps them not only understand the current expansion rate of the universe, but also how it expanded over a long time, allowing them to estimate how old the universe is now. Another way to find out the universe's age involves looking at a special event in space called Type 1 supernovae. While the cosmic microwave background gives a good picture of how the universe was billions of years ago, watching how the universe is expanding right now is another method. Type 1 supernovae are like cosmic dramas, where a star passes some of its stuff to a nearby white dwarf, causing a big explosion. These explosions, happening in a consistent way across the universe, are like markers for scientists. They are considered standard candles, which means scientists know how bright they should be. This knowledge helps them estimate how fast the universe was growing when these explosions happened. Scientists learn a lot by comparing how bright they expect Type 1 supernovae to be with how bright they are. This helps them understand how the universe was expanding at different times in its history. This method, started in the late 1900s, was a big deal in finding out about dark energy, a mysterious force that influences how the universe looks. It became a really important way to measure and study how the universe is growing and changing. Decoding the forces behind universal expansion. The Hubble Constant is like a measuring tool that tells us how much the universe has been stretching since the Big Bang, which happened around 13.8 billion years ago. You can think of the universe like a balloon getting bigger, but not at a steady speed. It's not just growing, It's speeding up like a car gradually going faster on a highway. NASA's discoveries in this area are not just about how fast this expansion is happening, but they're also trying to understand what might be causing it. If the expansion is slowing down, it could be because of something mysterious like dark matter putting on the brakes. On the other hand, if the expansion is speeding up, it might be because of something called dark energy, basically pushing on the accelerator. In January 2018, scientists found something really interesting. When they looked through powerful telescopes, they noticed that the expansion rate was not the same everywhere. The Hubble Space Telescope and the Gaia Space Telescope saw a faster expansion in the nearby universe, while the Planck telescope saw a slightly slower expansion in the more distant parts of the universe. The Hubble Space Telescope got its name from Edwin Hubble, who first suggested the idea of a growing universe. Back in 1929, this American astronomer was studying galaxies, especially those far from our Milky Way. He noticed that these galaxies seemed to be moving away from us. What was groundbreaking was his discovery that the farther these galaxies were, the faster they seemed to be moving. Astronomers thought this meant galaxies were just drifting apart, but as time passed, they realized something bigger. The universe itself was getting bigger. Picture it like being on a huge, stretchy rubber sheet. No matter where you are on that sheet, everything else seems to be moving away from you. And the farther something is, the faster it looks like it's moving away. This discovery completely changed how we see the universe. It's like solving an enormous puzzle where every single thing, from tiny atoms to massive galaxies, plays a part in this amazing story of expansion. And the fact that this expansion isn't the same everywhere in the universe makes it even more complex and fascinating as we try to understand the cosmos. Unveiling discordant views of cosmic expansion. Hubble made his guesses using the data he had back then, but now our technology is shot up. Telescopes like Hubble and Gaia are like cosmic detectives, always watching and improving how they measure things. Some telescopes use cosmic microwave background radiation to figure out the Hubble Constant, but this way has its limits, especially when it comes to studying faraway supernovas. That means our view of the distant universe is a bit blurry. Since we found out about dark energy 2 decades ago, scientists have been scratching their heads. The measurements we get from these different ways of looking at things, they argue about big stuff like how old the universe is and how fast it's expanding. Even though our technology is way better and gives more precise answers, it also shows us that things don't quite fit together perfectly. Trying to solve these disagreements by getting even fancier technology just leads to more questions about how the universe works. The differences might not seem huge, just about 10 to 20 million years, when the universe is around 13.77 billion years old, but in the grand scheme, they're a big deal. But fixing these differences is that maybe there are mistakes in how we measure the cosmic microwave background. The measurements made by tools like the Planck satellite, which gathered this information, have been checked a lot since they came out in 2013. They've been tested a bunch of times to make sure they're accurate. Another idea suggests that maybe we don't fully understand dark energy. It might not stay the same all the time. It could change over time, maybe even interact with dark matter, or involve something we don't know about yet. This possibility is really interesting to scientists, and they're writing lots of papers and theories to try and figure it out. Scientists are diving deep into understanding how the basic forces in the universe work. The differences in the measurements challenge what we know right now, pushing scientists to come up with new theories and experiments. Exploring how dark energy, dark matter, and other things might be connected opens up a bunch of possibilities, giving us a peek into how the universe changes over time. Using exploding stars to measure how fast the universe is growing, these measurements are tricky because understanding how these explosions work is complicated. If we don't fully understand the physics behind these exploding stars, it makes it hard to use them as reliable tools to understand the universe. A small mistake in how we model exploding stars could fix the big differences we see in how fast the universe is growing. The James Webb Space Telescope is supposed to completely change how we see space. It was supposed to help us understand a lot of things, like dark energy and dark matter, and also how fast the universe is getting bigger. But instead of making things clearer, the telescope's detailed observations have made things more complicated. The story of galaxies and elemental alchemy. Hubble made a groundbreaking discovery when he found out that the universe is expanding by looking at galaxies. However, the James Webb Space Telescope, by showing us amazing pictures of galaxies forming much earlier than we thought, has caused a big problem in the field. This challenge is all about how galaxies form and how they relate to their age and redshift. According to the usual way we understand the cosmos, hydrogen, a really important element, started appearing about 400,000 years after the Big Bang. This happens when protons and electrons combine. Before this, protons and electrons existed together, along with what would later become the cosmic microwave background radiation. After hydrogen formed, the universe mostly had a smooth gas of these atoms, mixed with helium and some background radiation. Gravity could do its thing in little denser regions of the hydrogen gas. These denser regions slowly collapsed, giving birth to the first stars in the universe. These early stars were mainly made of helium and hydrogen, the basic building blocks of that time. But things were about to change. The stars went through a process called nuclear fusion, a big change that allowed the creation of heavier elements like carbon and nitrogen. These new elements played a key role in forming galaxies because they absorbed heat, helping gas come together to create these huge cosmic structures. As the first stars in the universe reached the end of their lives and exploded, they scattered heavy elements into the surrounding gas. Each explosion, along with emerging black holes, sent out ultraviolet radiation that stripped electrons from hydrogen atoms, making the universe more transparent to UV light. New generations of stars continued this cycle, gradually filling the universe with heavy elements and UV radiation. These elements and radiation reached levels that allowed huge amounts of gas to come together and form galaxies. These galaxies became strong centers of gravity where gas collapsed, making stars and other cosmic things. While what we observe supports much of this story, there are challenges when we try to fit it into the bigger picture of an expanding universe. Figuring out how the early formation of galaxies, the birth of stars, and the overall evolution of the cosmos fit together is still a complex puzzle. It's a big challenge for scientists who study space, pushing them to improve and rethink our current models to better explain these observations and what they mean for the universe. Revisiting the Big Bang. The standard model we use in cosmology is really important because it connects the distances we see in space to how long it's been since the Big Bang. These distances are usually seen as fixed, direct values, but the age we calculate comes from theories about how the universe expands. This theory is based on Einstein's general relativity and what we know about matter from particle physics. It helps us understand how the distance or redshift relates to how long it's been since the universe began. But when the James Webb Space Telescope started looking deep into space and studying far-off galaxies, it found things that don't match what we currently know. It found galaxies that are much farther away and older than what the standard model predicts. Even though hints of this mismatch were seen before by the Hubble telescope, the James Webb Space Telescope made these findings clearer. The main problem is that the age of the earliest galaxies doesn't match what the standard model expects based on the redshift. These new galaxies we've spotted seem to have appeared much earlier in the universe's history than we expected. This clashes with the order we've established based on how old they should be according to their distance from us. According to our current models, these galaxies shouldn't have formed at such early times in the cosmos. This contradiction shows that we might be missing some key parts in our understanding of how galaxies came to be and changed in the early universe. The basic idea of the Big Bang theory, which says the universe is always changing and evolving, is still accepted. But with all this new data, scientists are being pushed to recheck and improve our understanding. The big question is, how much of what we know needs fixing, and what are scientists doing to dig deeper into these mysteries? To tackle these complex puzzles, scientists are using more advanced tools and methods to answer these big cosmic questions. One significant effort in this search is the Flamingo Project, a part of the Virgo Consortium. The Flamingo Project uses super detailed computer simulations to trace how the universe has changed from the very beginning until now. It's a big effort to understand how everything in the cosmos has evolved. This project gets funding from respected organizations like the European Research Council, the UK's Science and Technology Facilities Council, the Netherlands Organization for Scientific Research, and the Swiss National Science Foundation. These simulations create virtual galaxies and clusters, helping us understand how cosmic structures might have changed over billions of years. At the same time, advanced telescopes, like the Euclid Space Telescope and NASA's James Webb Space Telescope, are still gathering really important information about things in space. The main goal of these simulations is to compare the data they create with what these telescopes see. This comparison will help us check if the standard model we use for the cosmos is accurate. Scientists want to see how well these simulations match what we observe to understand if our model explains how the universe has changed over time. Professor Carlos Frank, a key contributor to the Flamingo research and a fundamental physics professor at Durham University, points out a critical moment in cosmology. He notes that right now, cosmology is at a point where the data from new telescopes doesn't perfectly match our established theories. This mismatch raises important questions about whether these theories are accurate or if there might be biases in them. To deal with these differences, making precise simulations has become important. Simulations mostly focused on cold, dark matter. Astronomers are giving more attention to including regular matter, which makes up only 16% of the universe, along with neutrinos, in these simulations to show cosmic evolution more accurately. Led by Professor JWST from Leiden University, researchers did a lot of simulations to study how the universe changes. They used a supercomputer called COSMA 8, which is part of the UK's Dirac high-performance computing facility. These simulations ran continuously for over 2 years. The goal was to understand the effects of both dark matter and regular matter, especially focusing on the regular matter's role. These simulations were complex and needed a huge amount of computing power, around 50 million hours of processor time. To handle all this computing work, the researchers developed a new code called SWIFT, because it spread out the computing tasks across thousands of processors, making the simulations run smoothly and effectively. Sometimes these simulations used up to 65,000 processors, showing just how big and complex the computing setup needs to be to study cosmic evolution deeply. Now it's time for today's subscriber pick. In a recent statement by Neil deGrasse Tyson, the James Webb finding ends debate in physics' shattering image. His perspective on the telescope's discovery suggests it's a game changer in physics, revealing things that challenge what we thought we knew about the universe. This calls for a reassessment of our scientific framework, but it's such a big revelation that scientists aren't sure where to start in reworking our understanding. To grasp the significance of this discovery, let's look back at how the universe started. Stars, black holes, and star clusters appeared quite quickly after the Big Bang, maybe within about 150 million years, possibly as early as 50 to 100 million years after it happened. These cosmic events were thought to be not so common, but the challenge comes from seeing more evolved galaxies later in cosmic history, specifically between 200 and 400 million years after the Big Bang. Astronomers usually figure out how old things are by figuring out how far they are from us, based on cosmology. Recent pictures from the James Webb Space Telescope show galaxies that are much farther away and therefore older than what our usual model predicts. This difference between what we expected and what we saw is a strong sign that we need to seriously update our current cosmological model. What do you think about this discovery? Let us know in the comments below. How science rewrote the rules of the universe. It can be unsettling to see our knowledge of the universe undergoing a big change, but history tells us that our understanding of science has always evolved through revisions and big shifts. Throughout history, how humans saw the cosmos changed a lot. In the early days of studying space, people thought Earth was at the center of everything, with stars and planets moving around it. This idea stuck around until the 16th century when Nicholas Copernicus challenged it. He suggested a new model where Earth and other planets move around the sun. This new idea completely changed how we thought about how things move in space. Later, in the late 17th century, Isaac Newton came along and brought a whole new level of understanding to science. He explained the forces that control how planets move, especially gravity. This was a huge leap forward in how we understood how things in the universe work. When the 20th century started, Albert Einstein came up with his general theory of relativity, which changed everything again. This theory talked about space and time as one thing. It was a really big change in how we understood gravity. In 1915, he said that gravity happens because mass bends the shape of space-time. Imagine a big object creating a dent in a sheet. The heavier the object, the more the sheet bends around it. This bending doesn't just affect stuff, it also changes how light moves. When there's a big object around, even light follows curved paths because space itself is curved by the object's presence. This idea, called gravitational lensing, was a key part of Einstein's theory of gravity. A famous physicist, John Wheeler, summed it up nicely. Matter tells space-time how to curve, and space-time tells matter how to move. This shows how matter and the way space is shaped are connected, explaining how mass affects the very fabric of the universe. The connection between matter and how space curves controls the cosmic dance in our universe. This curving doesn't just affect stuff, it also changes how light moves. When light travels, it follows a path called a geodesic, which can curve because space itself is curved. Think of a straight line on a flat sheet of paper. When the paper bends, that line isn't straight anymore. Similarly, the path of light, its geodesic, can bend when it moves through the curved space. This bending of light around areas where space is curved by big objects is what we call gravitational lensing. Before Einstein's theory, Isaac Newton described space and time as unchanging backgrounds where things happened. Newton did predict some bending of light, but Einstein's idea of space changing faced doubt and needed strong proof to be accepted in the early 1900s. Gravitational lensing, which was both observed and predicted, played a big role in proving that Einstein's theory, called general relativity, was right. In the early 1900s, people debated whether the Milky Way was the whole universe or just one of many star clusters. Edwin Hubble joined this debate by figuring out how far a fuzzy object beyond the Milky Way was. His calculations showed that our galaxy is just one part of a huge universe. Using what Einstein figured out, Hubble also saw that distant galaxies were moving away from us. This discovery showed that the universe is expanding. The Hubble Space Telescope, although not named after Edwin Hubble directly, played a huge role in improving these measurements. It's been a crucial tool for ongoing studies and exploration in cosmology. Moving forward in time, Stephen Hawking, a highly respected physicist, introduced an interesting idea. He proposed that while the universe might not be infinite, it doesn't have a clear-cut boundary, much like the surface of the Earth. Hawking also explored theories about how the universe might end, adding more depth to our thoughts about the cosmos and what its ultimate destiny might be. His contributions opened up new layers of contemplation about the universe and its future, bridging gaps in cosmic structure, understanding. At the heart of the cosmos, among the stars and galaxies, there's a complex puzzle called the S8 tension. This challenge in cosmology is all about figuring out how evenly the universe is put together and dealing with uncertainties about its structure. Despite the beauty of the sky, we're still unsure how matter is spread across the cosmos, leading to this puzzle called the S8 tension. This tension comes from differences in our cosmic data, especially in how matter is arranged in today's universe. Scientists are trying to solve this puzzle using a new computer simulation called Flamingo. Unlike older simulations that mainly focused on dark matter, Flamingo also considers regular matter and how its gravity affects the development of everything in the cosmos. The lumpy structure of the universe, represented by the S8 parameter, presents a major challenge in astronomy. Astronomers try to measure this parameter precisely by observing low redshift events, like surveys studying weak gravitational lensing. Gravitational lensing, caused by mass-bending spacetime, helps scientists study faraway objects, but there's a problem. The S8 values calculated from cosmic microwave background experiments don't match those from gravitational lensing studies. The CMB suggests a higher S8 value, leading to what we call the S8 tension. This issue is different from the Hubble tension, which focuses on disagreements about how fast the universe is expanding. The S8 tension is a whole new problem in cosmology. Despite using Flamingo's detailed simulations, which consider how regular matter, including extreme things like galactic winds, affects the universe, we still can't solve the S8 tension. We're not sure where this problem comes from. Some ideas have come up, from possible mistakes in measurements to maybe needing to rethink our whole theory of gravity. Simulations have shown something puzzling. At low redshifts, the universe seems less lumpy than we thought, challenging what the standard model predicts. But some measurements between low redshifts and the CMB fit perfectly with the standard model, hinting that the universe might have changed a lot over time. This interesting idea suggests that the universe might have followed our expectations for a while before going through a big change. It's possible that our current model still partly works, but we might need to update it to match these new observations. Scientists are still working hard to figure out how much we need to change our model, balancing what we already know with what we're learning about how the universe evolves. Thanks for watching, and we'll see you in the next one.